Welcome back, everyone. In this video, we will talk about the inclusion-exclusion principle. But first, we have to introduce some important terms. In mathematics, a set contains elements or members which can be objects of any kind. The union of two sets is a set containing all elements that are in A or in B. We can define the union of three or more sets, and in general, this is the formula for the union of n finite sets. The intersection of two sets, A and B, denoted by this symbol, consists of all elements that are both in A and in B. This is the formula for the intersection of n finite sets. The complement of a set A, denoted by the symbol, is the set of all elements that are in the universal set S but are not in set A. And finally, the difference or subtraction is defined as the set that consists of elements that are in A but not in B. Note that A minus B is equal to the intersection of A and B complement. Now we introduce the inclusion-exclusion principle. This principle is a counting method in order to calculate the number of elements in the union of n finite sets. We begin understanding the principle with an easy example. Let's say that we have two sets, A and B, and we want to count the elements in their union. This number is equal to A plus B, but we have to subtract their intersection as we have counted it twice. So the final result is A plus B minus their intersection. Suppose now that we have three sets. As before, we begin by adding A plus B plus C, and then we subtract their intersections. Notice though that we have subtracted twice the central region, which is the intersection of all the sets. Thus, we have to add it back so that the final answer is A plus B plus C minus intersection AB minus intersection AC minus intersection BC plus intersection ABC. We begin to see a pattern. What we actually do is that we start by adding all the sets, and then we subtract and add intersections of them alternately. Thus, we can create this table, which shows exactly why it is called the inclusion-exclusion principle. For your info, the general formula of this principle is this, although we will not be using it in any of our exercises. We give the following example as an application of the principle. Suppose that we have 200 bacteria and 60 of them contain the plasmid X, 55 contain the plasmid Y, and 40 contain plasmid Z. 10 of them contain both plasmids X and Y, 5 contain plasmids Y and Z, and 15 contain plasmids X and Z. Only 2 of them contain all three plasmids. The question is to find the number of bacteria that contain none of the plasmids X, Y, and Z. So there are two ways to solve this problem. In the first solution, we have to construct a graph, and we begin by drawing a rectangle which represents the total population of bacteria. Inside this rectangle, we draw three sets. The first set corresponds to the bacteria that contain the plasmid X. The second set corresponds to the bacteria that contain the plasmid Y, and the third and final set corresponds to the bacteria that contain the plasmid Z. So we have three sets in total, X, Y, and Z. And our universal set S, which corresponds to the 200 bacteria. What we actually want to find is the complement set of the union of X, Y, and Z. And this corresponds to this region of our graph. All right? We know that 2 of our bacteria contain all three plasmids. This means that the number of bacteria that are in the central region of our graph are 2, because this corresponds to the intersection of X, Y, and Z. Okay, the number of bacteria that contain both plasmids X and Z are 15. This corresponds to the intersection of X and Z. And since we have wrote down number 2 in the central region, we have to add 13 in order to reach number 15. So in the intersection of X and Z, we write down the number 13, so that 2 plus 13 is equal to 15. We follow the same process for the intersection of Y and Z. We have to add number 3, so that 2 plus 3 is equal to 5. And for the intersection of x and y, we have to add number 8. Okay? Now, in order to calculate the amount of bacteria that are in this region of our graph, we have to subtract those three numbers, 8, 2, and 13, from the total number of bacteria that contain the plasmid X, and that is equal to 60. So, in order to find the question mark, we have to subtract 8, 2, and 13 from 60. This is equal to 60 minus 23, and that is equal to 37. So the question mark is equal to 37. We follow the same process for y. We know that the number that we want to find is equal to 55 minus 8, parenthesis 8 plus 2 plus 3. That is equal to 55 minus 13, and that is equal to 42. So we write down number 42. And as far as the set Z is concerned, the number that we want to find is equal to 40 minus 13 plus 2 plus 3. That is equal to 40 minus 18, and that is equal to 22. Okay, so in order to find the final answer, we have to subtract all these numbers from the number 200. So the amount of bacteria that are in the set is equal to 200 minus, okay, this is going to be a tedious process, 37 plus 8 plus 2 plus 13 plus 3 plus 42 plus 22. All right, now I'm not going to calculate that. In fact, we do not need to construct a graph in order to solve this problem, because thanks to the inclusion-exclusion principle, we have a closed formula in order to find the final solution. In fact, we know that this number is equal to the amount of elements that are in the universal set S minus the union of our three sets, X, Y, and Z. Okay, now this, due to the inclusion-exclusion principle, is equal to X plus Y plus Z minus intersection X, Y minus intersection Y, Z minus intersection X, Z, and we add the central region, which corresponds to the intersection of X, Y, and Z. Now, this is by far more simple, and it is equal to 60 plus 55 plus 40 minus 10 minus 5 minus 15 plus 2, which is the number of bacteria that contain all three plasmids. That is equal to 155 minus 30 plus 2. That is equal to 127. So we subtract this number from 200, which corresponds to the set S, and the final answer is 200 minus 127, and that is equal to 73. So there are 73 bacteria that contain none of our three plasmids. That's it for today, and in the next and final episode, we will talk about the binomial theory and Pascal's triangle. Have a good day.